Hello everyone. Today we will talk about Monte Carlo methods for areal. So what we are looking at here is a Monte Carlo method applied to a simple grid plot, and let me quickly explain what that actually means. Monte Carlo methods basically work by running full episodes. That means we start from some state, take actions following a policy until the episode ends, and then we look back and see what rewards we collected. That total reward from any given point to the end is what we call the return. Now, important thing with Monte Carlo is it doesn't do bootstrapping. In other words, it doesn't rely on the value of the next state to update the current one. It just waits until the episode is over, then it goes back and updates all the visited states using the actual returns observed. And the idea here is that if we keep doing this across many episodes, the value estimate for each state will start to look like the average return we have seen when visiting that state. So it is entirely based on experience. And let's take a look at the grid. This is a 5 by 5 grid, 25 states in equal, total. Here you can see 3, 4 and 5. Okay, 25 states in total. Each record represents a state, and the numbers inside are the current estimated value of that state. And positive values show up in green, negative ones in red, and zeros or close to zero are white. As you can see, some states like here you can see that's pretty high, and here you can see, for example, 3.3, and it means in previous episodes reaching this state often led to decent returns. On the other hand, a few red cells show up to like I'm looking here negative 0.25, which suggests those paths have not gone too well. And we can see the current trajectory. And what is that? In this episode, the agent visited these states in sequence. Here, then the states, and back to the here, and then here the values. Okay, and right next to them, we have got the computed returns. Here we can see. So for instance, when the agent hit state 11, the return from there to the end of the episode was around 6.8, and that's pretty good. Meanwhile, state what we say state 13 shows a much lower return, about negative 0.80 78, and which is not promising. And you will also notice that some states show up more than once. You can see, and it is visited 3 times in this trajectory. Now this matters because we are currently using what's called first visit Monte Carlo. Here you can see now a visit MC, and now visit first visit MC. And what means is, first Monte Carlo is when we go back to update values, we only use the first time we see each state in an episode. So for state 12, we will only use the return associated with its first visit and ignore the others. And if we switch to every visit Monte Carlo, then we would include all 3 times. That changes the behavior of the algorithm. In some cases, it can help with variance, but that's something we will we'll see more clearly when we compare the results over time. Now going back up to the grid, you will see that some values are changing as episode runs, and that's because we are updating them after every trajectory. The update rule we are using here is a kind of running average. We don't just take the new return and overwrite the old values. Instead, we blend it with the old one, slowly moving the estimate as we get more data. And that's really the core of what Monte Carlo is doing here. It doesn't care what the environment dynamics are. It doesn't need a model, and it just learns by collecting returns and averaging them over time. That's okay, and algorithm flow is here. There are 5 main steps shown at the top. You can see, and the model cycles through each one of them as it runs. We'll go through them one by one. We start with generating an episode, and what does that mean? The agent starts from some state, takes actions based on the current policy, and keeps going until it hits a terminal state or until the episode is considered done. During this, we record all the states it visited, the actions it took, and the rewards it got. That's our raw experience. Next comes identifying the visited states. Now, if we are doing, let's make again first visit Monte Carlo, and I'm here, okay. We go through the episode and just mark the first time we see each state. That way, when we get to the update step, we will only use those first visits. The idea is that our many episodes, even the first visit alone, gives enough information to estimate the value accurately. On the other hand, if we were doing every visit, we will use all occurrences of a state within the same episode. And after identifying which states to focus on, we compute returns. For each visited state, we sum up the rewards from that point to the end of the episode. So if we visit state 7 midway through the episode and collect plus 3, negative or minus 2, and plus 5 or positive 5 from that point onward, then the return for that visit to state 7 is going to be 6. And once the returns are calculated, we move to updating the value function. This is where we take the return values and blend them into current estimate for each state. Usually it's done using a running average, something like new value equals old value times some weight plus the return times the remaining weight, and that way the estimates slowly get more stable over time. Since we are using first visit, we only apply that update on the first occurrence of each state in the episode. And there is policy improvement, final step. This is where we use updated state values to tweak how the agent chooses actions. And for that we use something called epsilon greedy, which just means most of the time the agent picks the action that looks best, but with a small probability epsilon, it tries something random. And let's stop on that for a second. You can see the slider here. Okay, it controls the epsilon value, which is currently, let's make it 0.3. That means 30% of the time the agent will explore. It won't follow the best looking option, but instead it will choose an action randomly. The remaining 70% of the time it will act gradually, picking the action with the highest estimated value. So this way the agent doesn't get stuck just doing what it already thinks is best. It gives some room to try out other possibilities which might turn out better in the long run. And that's the trade-off between exploration and exploitation. And we have a formula, and it's shown here, breaks it down clearly. If is the greedy action, give it a probability of 1 minus epsilon plus a little share of the random chance, and every other action gets an equal slice of the epsilon part. And before we move on, let's compare first visit and every visit Monte Carlo methods. And in first visit MC, like we said, we only use the return from the first time a state is seen in an episode. It is guaranteed to converge to the correct value, assuming we run enough episodes. But the trade-off is that it can have high variance because we are using fewer samples. On the plus side, it is easier to implement and reason about. With every visit MC, we use every time a state is visited in an episode, so we are including more samples. That usually lowers variance, which can help, especially in practical settings, but it might be slightly biased if the episodes are not long enough or if certain states are visited too often. So depending on your setup, either method could make sense. First visit is more conservative. Every visit gives you faster updates. And just to wrap this up, a few quick notes about Monte Carlo overall. It is model free, meaning it doesn't care about the environment's transition dynamics. It just learns from observed experience. And it is episodic. It only updates after full episode, so you need a way to define when an episode ends. It doesn't bootstrap, so it doesn't rely on the value on the next state when updating the current one. That makes it simpler in structure, but also a bit slower to converge compared to methods that do bootstrapping. And yes, variance is something to watch out for. Monte Carlo is unbiased, but in practice, the returns can vary a lot, especially in longer episodes. That's one reason why people sometimes mix it with bootstrapping methods later on. But this here, what we are showing is the plain Monte Carlo control loop using epsilon gradient policy improvement.